Good morning. How's everybody? Good. All right, so the quick announcement about movies for today. There's actually one about the Higgs boson at 11:15. We were just trying to look it up if this is actually particle fever that I was telling you about or something else. We're not quite sure, but could be interesting. Then there's KES, K-E-S. That one will be at 1:15. And then finally, Space for Repeat will be at 3:30 p.m. Thanks. Okay. So did anyone, yes? Yes, two quick reminders. One about cell phones. Please put them on silent. And also, I heard that there might be a watch alarm that's been going off during the lecture. If you have that, is it possible to switch it off? Just so that it doesn't wake everybody else up. Oh, I know everybody sleeps, right? Isn't that what lectures are for? No? All right, so today we're going to be, again, talking about how we see the Higgs. But this time we're going to be talking about seeing it using heavy particles. First, the usual slide where there's some more links for you. I just wanted to ask, has anyone managed to download some of the lectures successfully? Any problems? No problems. Okay, that's good. Because I heard some people had some trouble opening the PDFs, but hopefully that should be. So yeah, feel free. They're not changing the top ones, by the way. So it's just the bottom ones that are new. So if you have the top ones, that should be the same as before. So while we do that, any questions from last time that anyone wants to ask while people write it down? Yes?
There might be something big missing in the whole thing.
I don't think worried is the right word. I think that would be super exciting, actually. I think as scientists, especially as experimentalists, we want stuff to be wrong. We want to find things that we don't know. That would be great. So it's a bit what I'm going to talk about tomorrow, is give you some feeling for some of the problems that we have and why they're there. And most of the problems are really on the theoretical side. So it's with the theory itself that things just don't quite hold together. Experimentally, unfortunately, we found all the particles and they look pretty much how they should. But, of course, what we're doing there is we're trying to measure things more precisely. And maybe, as we do that, maybe something's going to pop out and say, hey, this doesn't look quite right. Because, yeah, things come either from the theoretical side or from the experimental side. It can be kind of either of them. Yeah?
So the Higgs field consists of all of the particles that the Higgs has decayed into. So when you... Is that right?
Nope. Sorry. No, so the way to think about it is that the Higgs field and the Higgs particle are the same thing. Okay? But once the Higgs has decayed, it makes other particles which are just normal particles. So for example, like today we're going to be talking about it decaying into Z bosons. Once it's decayed, those are dead standard Z bosons and the same as Z bosons that I might make any other way. So more you should think of it as being the same as the Higgs. But this duality between particles and fields is kind of a really weird concept because it's really the case that if you want to think about it as a field, you kind of need to forget about it being a particle at that moment. So you're sort of thinking about it as a field everywhere, and then, or you can think about it as a particle. It's a bit tricky to think about it at the same time, if that makes sense.
A bit like quantum mechanics.
It's exactly quantum mechanics. So, I mean, all the particles we're talking about, this is all quantum particles, and the mathematics that I'm not, of course, fully telling you, this is quantum field theory. So it's all exactly like quantum mechanics, just on a bigger scale. Yeah. Of course. Say that again?
Can you manipulate that Higgs field by creating?
Not yet. I mean, so the Higgs, right, as I told you, we've only made about 5 million of them so far. Okay, it sounds like a big number, but it's not a big number. It's a tiny number if you think about, how many particles inside an atom. And at the moment, we could only do it by just colliding things together at really high energies and sometimes making a Higgs. So we don't have much control at the moment. For example, I can't go out there and, fire 100 things and get 100 Higgses each time. So we're really in the early days. So far, we've managed to see it and learn a bit about it. We're way away from having control. This is something would be maybe many, many years away to see.
So what do you do with them?
Sorry?
What do you do with your 5 million Higgs?
They decay immediately, and we try and see them. That's been our whole project, has been trying to see the Higgs.
Create themselves and destroy
we create them, and then they disappear immediately, and then we look into the decays to see what we can actually see. Yes? No? Not exactly. So we have very precise predictions for what we should see, but we want to check that they're actually correct. It wasn't obvious that the particle we'd found was even a Higgs boson. We didn't know that at the beginning. So it's not obvious what we will get. We have a prediction, but that's the business we're in. Make a prediction, check, test it. So, yeah. Go ahead.
You say that the Higgs boson is always there in those particles, whether you look at it or not, or would you say that the collision creates the Higgs boson for that brief moment?
So the answer is both. The answer is both. Okay. So this Higgs field that you were asking about, that is everywhere all the time. Okay? So you need to imagine that even right now, throughout this room, there's a Higgs field everywhere, and there are particles that interact with this Higgs field, and that's how they're getting their mass. At the same time, though, when we make these collisions, we make a Higgs boson. And that's one Higgs boson, and it decays, and we study it. So it's kind of both, and again, it's going back again to this concept about duality between particles and fields. Okay, I'm going to stop now. Sorry. We're going to keep going with the lecture, but all questions can come at the end. This I won't pause on. It's just a reminder about reading material. And now let's just go back a little bit through what we did last time, especially the bits that are going to be kind of relevant for today. So we talked a bunch about the experiments at the LHC, and remember there were 4 of them. And the 2 that are most relevant for this course are ATLAS and CMS. So my experiment, this is ATLAS sitting down here, and this is CMS sitting at the top. And we talked a bit about the magnets, right? These are the dipole, they're called dipole magnets, which are actually in the LHC. By the way, a kind of fun thing, if you actually get to go down into the tunnel, you can just see the curvature of a 30-kilometer circle. So if you stand there and you look like straight down, it looks very, very straight. But then just at the end, you can actually see that it starts to curve. So it's really quite a big thing. And it's filled with about 2,000 of these. And yes, your company is involved in making these, right? Yeah. Yeah, you make the niobium coils, which are actually inside these dipoles. Yeah.
I'm going to ask a very naive question.
Sure.
That these magnets, they are not permanent magnets, they are electromagnets. Correct?
Mm-hmm.
That's obviously where the required energy is. But why do you say dipole? Because they need to be, clearly you need to generate 2 electromagnets with 2 different poles. So
they're actually superconducting magnets. So they're not just electromagnets, they're superconducting magnets. Remember I told you about the LHC being really cold. Now the reason you need that is otherwise there's no way to make such powerful magnets. It would be just simply incredibly impossible. And the reason that they're dipoles is because of what we want to do with them. Remember I said we wanted to bend the particles to go around the ring? It turns out the field you get from a dipole does exactly that. So it actually does them. We also use quadrupoles, actually, and we use octopoles and all these other ones. They're used for focusing. So this is, for example, when we need the beams to collide, we have to use these other magnets to do it. So it's just to do with what field you get, what magnet configuration do you want to have. And then we talked a bunch about particles, right? And we talked about the different types of detectors that we could use to see particles. And there are basically 2 main types. They're the trackers and they're the calorimeters. And last time we talked a bit about calorimeters. Today we're going to talk a bit about trackers, because these are going to be the detectors that we actually need for the particles that we're interested in. Then we talked about this representation, these Fineman diagrams, which you can actually use to draw different particle interactions. And I'm going to show you another one of them. So I just wanted to remind you about the pieces. There are the gluons, which are just like the curly hair. The quarks, straight lines. The Higgs, which is special, it's just a dotted line. And then finally, the other bosons. And of course, this is going to be the one we're going to need to use today, because today we're going to be talking a bit about the Higgs and the Z boson in particular. And a reminder that they may look like pictures, but these are actually equations. And so these pictures are actually representing different equations. And if you actually take the time to do the calculation, what you actually get out is the probability and the rate for something to happen. So if I drew one picture and I compared another one, did the whole calculation, I could tell you this is 10 times more likely to happen than this one. This is the information that's actually encoded in these diagrams. So this was Higgs, how we produced the Higgs via gluon-gluon fusion, and it decayed, again, via this top loop to photons. And this was something kind of important because we had to get around the problem that the Higgs is not actually able to decay to massless particles, right? Because the Higgs, again, as we said a few times, is the particle that gives elementary particles mass. It means it can't actually interact with particles that don't have mass. But we get around it with this trick where we put a top quark in a loop, and this means it can interact with the Higgs, and we can make what we need to have. Now, I realized I didn't actually show you this yesterday, so I decided to show you it today. These are two plots. Oh, the label's gone off one of the plots. That's very unfortunate. So what we're seeing here is we're seeing the mass of the Higgs. Okay? And it's actually the same in both the plots. And this is one from Atlas, and this is one from CMS. And the obvious thing that you spot is this little bump, right? You see this little bump, which is above this smooth background. These are actually the plots from when we announced the discovery of the Higgs. These were the two plots that you can have. And as I was trying to say, the thing that made me really convinced that this was real was seeing, and now it's very unfortunate the numbers are missing, that these two bumps were actually happening at the same place in terms of the Higgs mass. And so this was two independent experiments who had not talked to each other, made two huge detectors, calibrated them, end up getting exactly the same answer out of the two of them. And so this, for me, was very exciting to see. Okay. So now let's talk a bit about the Higgs and heavy particles. And for this, you might want to remember we were talking about how the Higgs could decay. And the answer was simple. It can decay to anything with mass. Now, of all the particles we were talking about, there were two categories. There were the bosons, and there were the fermions. And the point was is that the Higgs can decay both to the bosons and to the fermions. Now, the Z boson has a convenient name, since it's called Z boson. I think it's pretty straightforward to guess which of the two it is. And this is going to be the one that we're talking about. Again, I showed you this picture yesterday. We focused on this photon decay, which is this 0.2%. The one we're going to look at now is the ZZ decay, which is actually, again, a very, very small fraction. It's only 3% of the total decays. And what this means, of course, is that the Higgs decays to two Z bosons only 3 times out of every 100 decays. So if I make 100 Higgs bosons, I'm actually only going to get ZZ 3 times. This may seem like a weird strategy if you look at this plot, right? I'll come to your question in a sec. You see all these other ones where it's got a much higher chance of decaying to them, right? And you say, why don't we go after the ones that are the biggest? The point is, remember this thing about signal and background? It actually turns out that it's much better to go for these rarer ones because there are fewer background processes that look like them. And this is a very important thing because when you're designing your physics experiment, of course we make a plot like this and we think about it, but sometimes it ends up being that you have to go for something that they're very few, but you can do them very accurately compared to trying to look at lots of things and less accurately. A question at the back. Mm-hmm. And actually, you know those diagrams I was showing you? You can calculate them from that. So it actually depends on 2 things. So one, it actually is the case that it depends on the mass of the particle that it decays to. So as you might guess, it's not just that it has mass that makes the Higgs interact with them. In fact, particles that have more mass, the Higgs likes interacting with more. So you can imagine as the particle mass goes up, this becomes higher. But then there's a second thing, because I don't know if I mentioned it, but the mass of the Higgs boson is 125 GeV. Okay, we'll talk a bit more about what that means tomorrow. But some of these other particles, for example, the top quark, that actually has more mass than the Higgs boson. That one is 175 GeV. So the problem is if you only have 125 GeV and you want to make 2 times 175, you don't have enough energy. And so that's the second effect. So one is it likes the ones which have more mass, but if there isn't enough mass, then of course it doesn't decay to them. And so these 2 effects basically, from that you can actually calculate the whole thing of the rates of the decays. Yeah, it's kind of funny because in some sense it's a sort of easy calculation to do once you have all the bits of information, but then to check it, of course, is many, many people's work. So it's one that's harder to check than to predict, actually. Any other questions?
do you get a bottom and top quark if you can't get it from the Higgs? Some other way of getting it?
You mean in general when we collide the protons?
In general.
Oh, because actually there's a whole lot of things that can happen when we collide the protons. So I'm just showing you how we make the Higgs when we collide the protons. You can, for example, have two gluons who produce the top quark. And actually, by the way, top quark's pretty easy to make at the LHC. We make lots and lots of top quarks. We like to call ourselves a top quark factory. We make that many of them. Yeah, so that would be a whole other course about, but you can make all sorts of things. I'm just showing you one little piece. Okay, so then showing you how this looks in terms of the Fineman diagrams that we talked about. First thing you notice, the left half of the diagram is exactly the same. Right? This is exactly the same as we had for two photons. We have the two gluons coming in. We have the loop of the top quarks making the Higgs. Exactly the same. Then the other side is not the same. This is actually easier, by the way, in some sense, because the Higgs actually likes to decay to Z bosons. So we don't need any loop. All we need to do is we need to make two of the Z bosons. Has anyone been wondering why there are two photons and two Z bosons? Why not one? I just said that there were two, but I didn't really tell you why, did I? Nope. That's because I'm not telling you all the rules about these diagrams. There are various rules about conservation. One of the simplest maybe to think about is charge conservation. So if I start, for example, with a positively charged particle on the left, I need to have one positively charged particle on the right. I need to conserve charge. So all those laws of physics, right, you know, all these conservation laws, you actually have to apply them in the diagram. And that's actually why you need two. We're actually trying to conserve something. And if we have two, then we actually manage to conserve it. If we have one, we don't. So that's why there are some rules which actually go behind these diagrams. So that's what it looks like. Now, what is this Z boson? I mentioned it a few times, right? But now let's think a little bit more about it. Remember this picture that I showed you back on day one, which was showing you the four fundamental forces? And we talked about these two being easy, these two being a bit more strange, not so much in everyday life. Actually, the Z boson, he's one of the carriers of the weak nuclear force. So the Z boson actually does a whole lot of things. We actually need that because remember, for example, we need the weak force to actually get the sun to shine. So it's a very important particle which is actually part of that. And interestingly enough, there are quite some connections, for example, between the weak force and the Higgs. Because the reason we needed to have the Higgs was the problem with just this guy, the Z boson, having no mass. So he was one of the particles that, in a sense, predicted that we needed to have the Higgs boson. So, of course, it's very important to see, does the Higgs actually interact with this particle? Because if it didn't, then we know our theory was definitely wrong. Right? We have this particle, it's meant to be giving mass to our Z boson, and it doesn't interact with it. Oops, we've made a mistake. And so this is why this was one of the very important channels to understand if our theory was really correct. So that's on the theoretical side. In a sense, experimentally, Z bosons are really easy. In fact, they're probably, if someone gives you a data set of data from the LHC, you can do this, by the way. There's lots of data out there. Probably the first thing I would get you to do is go and find some Z bosons. With about an hour or two of work, you can go see Z bosons. They're pretty easy. Now, the way that they decay, because they feel the weak force, they actually rarely decay to all particles which feel the weak force. Okay? Sort of similar idea to what we were talking about with the Higgs. But every so often, again, it's going to be 3 times out of 100, it actually will decay to a pair of electrons or a pair of muons. Here it actually illustrates quite nicely what I was telling you about conservation and charge, because the Z boson, he actually has no electromagnetic charge. He's neutral. Okay? And if you decay just to an electron, oops, this one's the electron, you'd have negative charge. So actually what he decays to is an electron and its antiparticle, which is the positron, and if you add together the plus and the minus, you get back to 0. And so this shows you quite nicely why you might need to get 2. And actually he can decay to electrons, also can decay to muons in essentially exactly the same way. The bad part about this is, remember I told you that it was pretty rare for the Higgs to decay to Z bosons. So now we took something that's pretty rare, and then we took something that's pretty rare again, and want both of them to happen. So remember some probability theory, when you need to combine these together, you can guess that this means that it's going to be very rare that this happens. It's going to be essentially the product with a few corrections that you need to put into. It ends up being on the order of 1 out of every 10,000 Higgses that we made. Yeah?
The free spin particle that bosons, are they all neutral?
Nope. So for example, I've been talking now about the Z boson. It has this brother, the W boson. The W boson is charged. And so there are two W bosons, a W plus and a W minus. So it depends. They don't have to be. But of course, if they are neutral, what that means is they don't feel the electromagnetic force. Right? If they are charged, then they feel both the electromagnetic force and the weak force. So they work in different ways. So one good thing, though, is that we can actually combine these two together. Oh, sorry about that. You can take 4 electrons, so you can have both Z bosons decaying to electrons. You can have both decaying to muons, or you can have 1 decaying to electrons and 1 decaying to muons. By the way, it's not allowed to decay, for example, to 1 electron and 1 muon. This can't happen. This is, again, one of those conservation laws that would actually break. So it needs to be of the same lepton flavor. That's actually what we call it. Flavor is electronness or muonness, this sort of thing. And so this means that this decay is actually much, much rarer than what we were talking about for 2 photons, right? Much lower probability for this to happen. So we go back to our Fineman diagram. This is the same one that I showed you, but now I added some more on the right. And what I've added here is the decay to leptons, to electrons or to muons. And I didn't label it, so we can actually consider all the different options. And now you can see how these diagrams can be kind of useful. Once I've finished, I just need to look on the right-hand side here, and that tells me all the particles I expect to see in my detector. Right? There's a whole bunch of complicated stuff going on here, but as an experimentalist, I just need to worry about looking for 4 electrons, 4 muons, or 2 electrons and 2 muons. It doesn't exactly matter how they actually got there. So now I wanted to talk again about signal and background. And the example I want to use is, imagine you have a big bowl of Smarties. Okay? It's a very simple example, but hopefully it works. And let's pretend that you absolutely hate all color Smarties except the red ones. Okay? You just don't eat them. Now, you have 2 options. You can either choose this bowl, or you can choose this bowl of Smarties. Okay, there are more Smarties in this bowl, but you don't like them because they're not red. And what's obvious here when you look at the 2 pictures is it's much easier to find the red one if you have few other Smarties around than if you have a whole lot of them, right? You just have to dig through and find it. And this is exactly the idea about signal and background. If you have fewer things that you don't want, it's much easier to find the thing you're looking for than if you have lots of them, right? And this is the idea. This is, again, what I was trying to say about why this is actually a good way to look for the Higgs boson, perhaps even the best way to look for the Higgs boson, even though there aren't very many red Smarties in total.
Can I ask you something?
Of course.
Is the proviso then that ratio of the small number to the larger number must always be the same, or is that not critical? In other words, it really depends what you're looking for.
So the small and the large are the signal and the background. These are the way we like to refer to them. And actually, this is something you optimize when you make your analysis. So the higher signal to background ratio, so it's really just the ratio of the 2 of them, the easier it is to do your study. So you always try to make it as high as possible. There's one caveat. If you make it so high that you don't expect to see any events, it's not very useful. So I could design an analysis, right, where I expect to see, no background at all and 0.001 signal events. That's going to be a pretty boring experiment because I'm going to see nothing. And it's not. So that's the other side, is you need to have enough signal, but then you want as best a signal to background ratio as you can get.
So I'm correct that the arrowhead on the Muon symbol, on the quark symbol, so the symbol
Oh, it is. But it is telling you, so I haven't told you everything about Fineman diagrams. So there is a time concept in Fineman diagrams, right? So remember when I've talked about them, I've been talking about starting on this side and coming to that side, okay? So there is a time concept. It's not the case that we start here and go that way. The arrow is actually indicating a particle when it goes forward, and when it goes backwards, it's showing an antiparticle. Because it turns out that when you write the equation, if you take an antiparticle and make it go backwards in time, you take a particle, make it go backwards in time, that's exactly the same as an antiparticle going forwards in time. Just in terms of mathematics, before everyone thinks I'm crazy, I'm just talking about mathematics here. I'm not talking about going back in time, really. So yeah, that's what the arrow means. And some of them don't have arrows. These are the bosons. They do not have arrows. And this is to do with exactly how they work. They have a different property. Yeah, you can play around with time. It can get confusing. You have to be a bit careful with that. Okay. So this is kind of what I tried to say, is that despite this very small decay rate, it's very powerful. And the reason that the background is low is because there's a very low probability, if you think about all the other collisions, right? You know, we were talking about making top quarks. That's actually one of the backgrounds, by the way. And all the other processes, it's very unlikely that you actually make 4 electrons or 4 muons. This is lucky. It just happens to be. It's very rare. And this is why you end up having few of these background events that look like your signal. And so if maybe you've heard the term golden channel, this is the one that's called the golden channel, just because it's by far the cleanest channel that we have at the LHC. All right, enough theory. Let's talk about what we can see. And this is a similar picture. This one's actually of CMS to what we had last time, which is showing all the different bits of the detector, okay? And the way we like to show this, of course, is we show you how it looks for different particles going through. Now you can guess which particles we're interested in today. Okay, today we're interested in electrons and we're interested in muons. That's what we said our Z boson's decaying to, so we better find those electrons and muons that it decays to. Probably the easiest one is the muon. We talked about it yesterday about how muons don't interact very much. So the way that we actually see them is we see that they go all the way through the detector. And we put some special detectors. These are actually the muon detectors in CMS. And this blue is showing you where the muon is actually interacting with them. And the only particles that get out here tend to be muons. So if we see something there, we're pretty confident that it's actually a muon. And so that's the idea. For electrons, on the other hand, so these are these little red ones here. What we're after is actually seeing something in our tracking detector. So here's our silicon tracker. And then we want it to lose all its energy in the calorimeter. So what happens is you have a track and you have all the energy lost, and you can tell it apart from the photons that we were talking about yesterday, because photons have no charge. So they don't leave a track, they just leave the energy within the calorimeter. And so that's the idea about how we're trying to see these electrons and to see these muons. So now we're going to talk a bit about tracking detectors, okay? And so what I mean by the tracking detectors, before I do that, I'm talking about the silicon tracker. I'm actually also talking about the muon detectors. They have, in some sense, the same concept between the two of them, even if the technology that we tend to use is very different between the two of them. So the basic idea is kind of like when you go and you want to go and see wildlife, right? The idea of it is you actually want to see it, but you don't want to disturb them, or you want to disturb them as little as possible. It's exactly the same idea with the particles. We want to measure their trajectories, but we don't want to disturb them too much by our measurement. If we do that, then we're only going to see what we did, not what the particle originally looked like. And so this is the sort of difficulty, in a sense, in tracking detectors, because if you disturb it a lot, it's much easier to measure, but then you're measuring something that's not very interesting. So this is a bit the conflict that you have in terms of the design. Now, I don't know who was paying attention and noticed all the curvy lines and the straight lines in this picture. Is anyone wondering about those? Why some of them, and it's not a mistake, by the way, that they're curvy and straight. In fact, it's actually very important. The reason is, remember we talked about making the accelerator and how if we put particles in a magnetic field, we would actually bend them, right? The right-hand rule, we can bend them. So actually what we're doing in these detectors, and now again I'll go back and show you this, is notice this piece sitting over here. This is actually a large magnet, and this one's actually a solenoid, so we use all different types of magnets. And this solenoid is making a magnetic field all the way inside there, and because we have a charged particle, they're actually following a circle. So that's what you're seeing, is you're seeing a particle following a circle because it's already in this magnetic field. But there's an extra trick. It turns out that it's not just the case that you get a circle. Actually, you can get many different circles. But the very convenient thing is that it turns out that how much a particle bends depends on the momentum. So if you have a very, very energetic particle going through your detector, it goes almost straight. If you have a particle which has much less energy, it actually bends a lot. And so these are just showing you sort of how it might look from something with high momentum down to something with low momentum. And the reason for this is because you have one constant magnetic field. If you changed your field, this would look different, but we fix our field and we keep it constant at one value. And so what we actually do with this is we use this to measure the momentum of the particles. And it's so basically by measuring the curvature, and it's really as simple as actually measuring the curvature, this directly tells you what is the momentum of the particle. Once you know its momentum, then you know everything you want to know about it. And so that's actually what trackers are trying to do. They're not just trying to see particles. What you're also trying to do is to measure the momentum, and that's again this point about trying not to disturb them. Because if you, for example, hit a wall, your momentum will change completely from the original value. Sorry about all the coughing.
So is V in this case C in all cases?
It doesn't really matter because it's very close to C. For some of the very heavy particles, it's not quite. But we always used to use relativity in all these calculations. It's always close enough to see that relativity is a very important effect. Yeah?
What happens to the particle at the end of the bend?
Oh, this was just, I stopped drawing it. The reality is that a particle will keep going unless something happens to it. No, once it passes out of the field, then it will go in a straight line. If it hits something, this is normally what we're trying to do, then the particle's destroyed and gone. So normally what happens is all the particles we produce in an LHC collision, they're normally absorbed in the detector material. So none of them would get to the surface, for example. The one exception is neutrinos. These will keep going, actually. They don't interact very much, so they essentially just keep going forever. So yeah, particles don't disappear. They have to either interact or they have to decay or something like that. Otherwise, they just keep going. I don't know if you noticed one other thing in this picture. It's kind of a nice picture. Did you notice the blue line, the muon, does something weird, right? It flips direction. The reason for this is you see these red bits sitting over here. These are also a magnet. And it's actually going in the opposite direction. So what you're seeing is that you're seeing that we flipped the direction of the magnet, and this means the curvature of the particle has actually flipped from one side to the other. Oh, this is actually for convenience from a detector side. So the point is there's a massive current in this magnet. So CMS has a 4 Tesla magnet here. And you actually need a return yoke to get the current to come back. So it turns out to be convenient to use this one to come back. Sorry. This cough is very annoying. I can't talk. All right. So now we want to talk.
Would you like a sweet?
Oh, sure. I'll take sweets.
My wife says it works well.
Yeah, no, I caught this from my niece, unfortunately. So she's a lot more unhappy than me. She's 2 years old. Okay, so this was about Oh, this is not very easy to open. We talked about measuring the momentum, but it's actually not straightforward to even figure out what curves to draw, right? Particles don't draw us nice curves. They only give us information when they hit a piece of the detector. So here we imagine, here's our nice little toy detector. And again, we have a particle going through with nice curvature because it's a magnetic field. This is actually what it might do. So the little yellow dots are the particle interacting with the detector. So then this is actually what we get out, a picture like that. And the task that we need to do with our algorithms is to figure out this is what happened. So it's really starting from all those little dots and going back. Of course, it actually looks a bit more like that. So this is actually showing you the tracks after we run the algorithm. But this is showing you what it looks like in Atlas when there are a whole lot of tracks here. So it's not the case that we just have, 3 nice little hits, we draw a line. The actual case is that we have this huge detector filled with all this information, and so the algorithms are pretty complicated that we have to use to do it. So let's talk a little bit about silicon detectors. Those are the innermost ones that we tend to use. So silicon is a semiconductor, and the way this works is it means that electrons need a certain amount of energy to be able to move freely. Semiconductors are exploited extensively in modern electronics, and so here are a couple pictures I got. This is an Intel wafer, actually a pretty old one. And this is a slide showing you a little bit what it can look like on a silicon chip. And this was meant that the particle physics community kind of kicked off a lot of this stuff, but at the same time has profited greatly from the fact that this is used everywhere. We use all sorts of commercial solutions to be able to build our detectors.
So did CERN develop the semiconductor?
No. No. We just develop specific applications. So there are certain applications that are needed specifically for particle physics. In particular, we need very radiation-hard detectors, which is not something that other people use. So this is something where we actually end up leading the technology. Commercially, they've by far overtaken us. So
Did it come to you for advice then? Texas Instruments?
no, they'd come to us to test out their things. So the way we actually use things are still much heavier than many commercial applications. And it varies precisely what. So the thing that CERN did invent was the World Wide Web. This one actually was started by a physicist at CERN. He's no longer at CERN. I think he gets paid more. And it was basically because he actually wanted to talk to his colleagues and to be able to collaborate over large distances. Of course, the World Wide Web has been completely taken away. It's overtaken by commercial interests. But this is the whole idea. Everything CERN does is public and open, and we don't take any money from this. Right? We have ideas, we give out our ideas, and if people want to use them, then they can use them. So this is kind of the philosophy, and it's important because our research is supported by governments. And so there's no way you can take money from the government and then start making your own company based on the money the government gave you. You need to give it back. This needs to be free and needs to be open.
So what you need is a commercial manager.
This would change the structure completely.
Corruption.
It would be even, I think, worse. It would be theft, actually, I believe, if we took it. But anyway, let's talk about semiconductors. So this is a little bit of a sketch showing you some different types of materials. Okay? Probably you've heard about them. You've heard about conductors. You've heard about insulators. And then, of course, as you might guess, semiconductors are going to be somewhere in between the two of them. And here, on this axis, is going to be the energy that you need to get from two different places, from the valence band into the conduction band. And the thing about an insulator, and remember insulators are great, this is what you want to use, for example, if you don't want to get struck by lightning, if you don't want the current, is there's a large distance between the valence band and the conduction band. And this is actually what gives it its main properties. On the other hand, if we look at a conductor, the two are overlapping. And so here, this is very easy for current and charge to flow through it. Semiconductors, on the other hand, as I said, they're in between. There is a small distance between the two of them, such that they're not quite conductors. So it's not like, the electrons can move around freely, but there's just a small bit of energy. So it's quite easy to give it the small energy to be able to do the same. So here's a little bit of an example about how we actually do it. So this is meant to be a slice of silicon. So imagine you're sitting right in the middle of one of these detectors, and you have a slice of silicon, which is, of course, a semiconductor. You have an electric field, okay, which we're applying over there, and some particle is passing through your detector. Actually, this will work well. When it passes through, what it's doing is it's interacting with the silicon, and it's producing electrons and positrons, okay, as it goes through. Now, because we have this electric field, what happens is that the positrons go one direction and the electrons go the other direction. That's because they have opposite charge, so some of them go up and some go down. Then we connect our electronics to the side of this, and we actually collect up that charge that is produced and read it out. And what this tells us is, firstly, a particle went through, and also we can count how much charge there is, which actually tells us a bit about how the particle, how much charge it actually deposited. And that's the basic idea. The details of it get a bit complicated, and these things are really, really tiny. Like in Atlas, for example, we have almost 100 million individual pixels, because you need to make them very small. But the principle about how it works is really the same as this. Yes?
What's boggling my mind with this, you said something like 1 million collisions a second. So now you've got billions of particles coming through every second, 1 to every nanosecond.
Bit faster.
How do you work out, and each of them decay into many particles, how do you work out that those two came from that collision and those two came from that? It just seems boggling.
This is a whole lot of work, so it's an excellent question. So first of all, the collisions are separated by 25 nanoseconds, okay? So if you actually calculate it. And the particles travel at the speed of light for our purposes. This actually means there's about 30 centimeters between them. Okay, so you have one collision, the particles all move out at the speed of light. Next collision, those particles are 30 centimeters behind it. Okay, so there's a physical separation between the two of them. Then the second bit is what I was talking about, the trigger, which I mentioned a little bit, I think, yesterday. We don't read out every collision. So every collision those particles are made and go through the detector, we don't record them. What we do is we figure out which is the interesting collision, and then our detectors are smart enough to store the information separately for each collision, such that we just read it out from one of them. So for example, we would know where the particle should be at that time, and then we use that just to get that information out. There is a little bit, sometimes you get a few particles from an extra collision, which kind of can leak in, but it's a very small effect. So we're largely successful in being able to do that. By the way, what's actually a bigger problem is the fact that it's not always one proton that collides with one proton in each collision. Remember I told you there were lots of protons in each of the bunches? Actually, it's about 40 on average that collide each time. So the real trouble is figuring out which is the interesting one out of all those 40 collisions that all happen at the same time. This is the one that causes us quite a bit more work.
So the pixel size of each one of these
Pixels.
points is very, very small.
Yeah, so it's typically 25 microns by 100 or 50 by 50 microns. That's the size of a pixel. And you want this to get, because you have all these particles that we're talking about, if you don't make it small enough, you're going to have like 1,000 particles going through the same one. It's not useful. So you make it, basically you make it as small as we can, and we're limited typically by the bump bond technology. So this is just how you connect the electrical wire to the pixel. You're actually not able to go smaller than 25.
Sorry, just how does that relate as a ratio to particle sizes?
Oh, particles are essentially point-like. So the particles are point-like, so they mean they have no size. What you actually worry about is not really the size of the particle, the density. So what you're optimizing against is how likely am I to have two particles that close together. That's the thing that you care about. The particles are effectively have no size, at least in everyday terms.
So you use probabilities to decide on whether the particle that you think it is the one that it was.
Oh, it's a whole long story about how you decide. Yep. And sometimes you get it wrong, and that's okay. We try to account for that. So that was a little bit on the sort of small size, what it looks like. These are actually what they look like once you build them up. This is the Atlas tracking detector. It has various different parts. This is the pixel detector. So the pixel detector is about this big. And remember, this is a detector sitting in the side of that colossal Atlas detector. So this one's tiny. It's actually what I worked on for a long time. This is the tracking detector, the SCT, and these are all silicon again. You see these sort of shiny things? These are all the modules. And the pixel detector goes inside that one. Remember that metaphor of an onion? Now we're really looking at the center of the onion to see these detectors. CMS is the same thing, exactly the same idea. This is their pixel detector. Okay, it's half their pixel detector. Of course, there's another half that goes on top. And this is their tracking detector. And you can see that these look very similar. And that's because both of the experiments are using a very similar strategy in terms of this to actually see the particles. So let's look at the report card for silicon detectors. So the benefits of them is what we were talking about, the very high granularity and the precision with which they can measure things. They're also pretty good under radiation. Problem is, these things that sit right at the center there, they see all those particles produced from the collisions. And it's actually enough that it's highly radioactive. So you can't just put anything there. It would actually destroy many things that you would put right in the center there. So it needs to be highly radiation tolerant. Disadvantages, though. Silicon is actually quite dense. And so this actually goes against what I was telling you about trying not to disturb the particles, trying to measure their momenta without actually influencing them. So this happens. It's also pretty expensive. You actually measure the detectors in terms of meters of silicon, and this is something that can easily cost a huge amount of money. So those are the pros, those are the cons.
But silicon's not expensive.
It's expensive when you want many meters of it. We're talking in the tens of millions. This is the scale for building these sorts of detectors. You also have the electronics as well, which I haven't really said too much about. These are not cheap either.
On the question of cost, what did it cost to build
The LHC? So as I said, the accelerator is the most expensive thing. So this is in the order of billions for an LHC. The detector's on the order of millions. Oh, Swiss francs, but does it matter when I'm talking order? Oh, it does. Rands would be very different. That's true. Yeah, rands would be different, but dollars, Swiss francs, euros, all pretty much the same on that scale. So it's interesting because the detector is a small part of the cost. It's really that accelerator, and it's the magnets, by the way. The magnets are by far the driving cost of the whole project, and so that's why that's where a lot of investment is made, because you can make it a lot cheaper.
These magnets, are they copper coils?
No, they are niobium titanium, these ones, and nowadays they're investigating to see if there are other alloys with niobium. I've heard about it. Niobium tin might be a possibility for the future, but he would be by far the expert on this topic.
Well, silver is
Sorry?
They don't actually make it as an alloy.
Okay.
If you think of a pencil, say Exton, make a rod of niobium, a rod of other material. Niobium is very brittle, and so you want to be able to have something you can work with. So it's like a whole lot of pencils, put all these rods together, and you extrude that down to the thickness of one pencil again. And you put a whole lot together again, and then you extrude that. You keep on extruding it until you get your conductor, which is thousands of little diagrams. Then you etch the supporting material off at the end, and you get a tuft of what's like hair, and that's your connector. That's what you're connecting into. And you put it into, must be lower than -60
Mm-hmm.
in order for it to go superconductive. So just making one of those conductors is about 50, 60, 70 extrusion processes.
It took a long time, very much a long time. Actually, they have some extra niobium titanium. You can buy a keyring at CERN, which actually has some piece of the LHC.
They make a lot of them because everybody uses a CAT scan.
Mm-hmm.
Effectively using a smaller one at the same thing. And they also, even the ones that you put in the hospital, you have to work at -60.
Mm-hmm.
Like
Because remember, it needs to be, when something's superconducting, right, we need to have zero resistance, right, to actually, that's what superconducting means. And this indeed was the problem that happened at CERN back in 2009, where one of the connectors effectively became slightly non-superconducting. And this was actually, they made an explosion.
If you get any magnetic effects in it, there's been oscillating field in it. So you can make sure all your connections.
Yeah. All right. Away from the LHC, back to detectors. We're now going to talk just for the last little bit about the other type of detectors, which are gas detectors. This is the other type of tracking detector. The idea here is, this is meant to be a tube. So imagine a long silver tube. This is what they tend to look like. And what you do is you fill it with some sort of inert gas. It can be something like argon, something like xenon. This is a typical gas that is used. Now what happens is, again, when you have a charged particle passes through, it's going to look awfully familiar, it will actually ionize the gas. And again, this means we produce electrons and we produce positrons. Now what we do is we actually have a cathode and an anode. There's actually a wire going through the middle of your tube. And then usually the outside of the tube itself is also either the cathode or the anode. And what we do then is we collect up the electrons, we collect up the positrons, and again, in the same way, we can actually use this as a measure of a particle passing through and also how much charge it actually deposited. The big advantage about gas detectors is that they are much lower cost and much lower density, right? You're filling something with gas. Gas is going to have by far lower density than silicon. However, of course, they also have lower precision. And so that's the reason why we tend to use them for muon detectors, which is really out at the side. These are enormous. If we tried to make them out of silicon, we would spend actually billions on making our detector. Whereas here, we can afford less precision, because if you think about it, you have two very dense particles. By the time you get many meters away, they're going to be far apart. So you need much less precision as you actually move out in the detector. And so it's the right choice. So this is CMS's muon detectors. They're enormous, by the way. These are the things really on the outside. So you've got to imagine some tiny little person standing next to them. And similarly, these are Atlas's ones. Here you can actually see the tubes that I was telling you about. These are the little gas-filled tubes which actually show you where the particles go. So now back to the physics. Now we know how to find electrons and we know how to find muons. This is actually a real candidate event. By the way, I always say candidate event. I don't say Higgs boson. That's because everything is probabilistic, right? It has a good chance of being a Higgs boson, but it might actually just be background. So that's why it's called candidate. Here you can see, for example, that we have 4 electrons. You can tell that they're electrons because, okay, you can't really see the track. Well, the track is actually colored in red and blue. But you can notice they're depositing their energy in the calorimeter. This one has actually gone kind of forward, like along the direction of the accelerator, and that's why you're seeing it depositing energy over there. One other important fact, they all have to come from the same spot, right? We want them to come from one Higgs boson, which was produced there. If they were coming from here, we'd know it came from a different particle. So that's another important piece. Another example, this is again a Higgs candidate event, this time decaying to 4 muons. So it's maybe easiest to look at this projection, which is the slice vertically through the detector. And you see these 4 nice tracks coming out. Here, it's looking sort of into the detector. And here you see the little tracking detector, and you see the muon detectors really big out here. And these ones which are in color is actually showing you which bits of the detector the muons actually hit. And again, just like for the electrons, they're all coming from the same spot in the detector. Final option is the candidate event with the Higgs decaying to 2 electrons and 2 muons. Same idea, this time we need just 2 electrons and we need 2 muons that we can see. By the way, this isn't actually how we do physics analysis. So it's not the case that I sit on my computer and I look at pictures and I say, yes, I found a Higgs boson. No, I didn't. Actually, we do our whole analysis, we finish it, we have the result, and we make these pretty pictures to try and explain to people what we saw. Just to tell you. In the old days, it was how you did it, actually, and there were whole teams of people who used to look at the pictures that you would actually take out of detectors. Now computers are much better than us. They can spot patterns much better. Uh-oh, hold on. We're about to lose a computer. Oh, there we go. Okay, so now I have the same little video as last time, and this time it's going to show you what it looks like for the Higgs decaying to 4 leptons. Remember, you want to keep your eye out over here at 125 GeV. And it's just like the photons, you see all the events coming in. In this case, the shape of the background, which is the red guy, is not smooth. It has a shape, and we understand this shape quite well. But what you should be noticing is this guy that's popping up over there, where you see that the data is actually larger than the background. And now we say, hey, let's see what we see, and we put in a Higgs boson. So you can notice this looks very different to that 2-photon one we were looking at, right? That had the smooth background going down. But here, you can also notice it's quite a lot easier to see the signal compared to the lower background that we have. We'll watch it again. You can also look at the ratio. The ratio is really quite nice. That's where you can see quite clearly the peak of the Higgs.
Is this in real time?
No. So this was over 9 months. And again, this was made afterwards. The reality was that we were analyzing on our computers, and every couple of weeks we'd have a look to see what we saw, to see it. Okay. So what happened is that it was in midway sort of through 2012 is both Atlas and CMS had these bumps. Okay, we hadn't seen each other bumps, but we thought, hey, this is pretty exciting. Most likely we've seen something. The way it works at CERN is if you think you've discovered something, you have to actually go and talk to the Director General and tell her, she's a woman at the moment, that you think you found something, you'd like to have a seminar. And the way it works is you then give notice to the other collaboration, and they have 1 week to decide if they have something or not. So this is trying to make it be fair, that both can say something between it. Of course, in this case, both of them had something, so it was pretty easy. And there was a schedule, the seminar, which was actually scheduled. And this is the seminar itself. And here you can actually see this is a spokesperson from CMS, Joe Candela, giving his talk. And this is Fabiola Giannotti. She's our current Director General. She gave the talk on behalf of Atlas. And this is what I mentioned, where I saw for the first time the CMS plot. And this was really, really exciting when we actually saw, hey, this looks like we've actually seen something. It was published on the cover of one of the physics journals. So this is Physics Letters B. And this is the plot from Atlas. Here you're looking for this nice dip. I haven't explained how this plot works. And here from CMS, that's the one you saw, where you see the nice bump, essentially showing the Higgs. By the way, you saw the background. It's the same background I showed you, with a nice view of Mont Blanc. Now, what actually happened is that in 2013, the Nobel Prize in Physics was awarded to Peter Higgs. This is the guy the Higgs boson is named after, and Francois Englert. It probably would have been awarded to Braut as well, but he'd actually died beforehand. And the Nobel Prize is never awarded posthumously. So that's why it was these two. It was a bit of a debate. There were a bunch of theorists all involved with the Higgs. So it wasn't a straightforward one, because a lot of people came up with the same idea at the same time. It was also a bit of a debate about whether it might be awarded to the experiments as well, because of course these are the theorists. But historically, the Nobel Prize has only been, in physics particular, only awarded to individuals, never to collaborations. And in the case of Atlas and CMS, it's really not possible to identify specific individuals who found the Higgs. It's really a result of a large group of people. So that's why it ended up being given to the theorists. But as someone said to me afterwards, today you're feeling a bit sad because you didn't get a Nobel Prize. Isn't that pretty cool that this is actually something you were even thinking about? That we might have even been considered for one. And so, yeah, I thought this was a very exciting day.